Hello everyone. So this week we're actually going to double up on notes, but don't worry, it's very short and most of you have seen this information before. So this very short set of notes is about electrons and waves, or electrons as waves in certain cases. So the first thing I want to do is just go ahead and define spectroscopy, which is the study of the interaction of electromagnetic radiation with matter. So for the most part, I am going to abbreviate electromagnetic radiation here. And the reason that I'm going to do that is honestly pure laziness, because I don't want to write out electromagnetic radiation a bunch of times. And so I'm going to refer to that as EMR most of the time. So matter can do a few things with EMR. It can absorb electromagnetic radiation. So if we have a piece of matter and that EM wave is being directly absorbed by that piece of matter, sometimes it can move that piece of matter, or that atom, from a ground state, which is its normal state of being, to an excited state, which basically means the electrons in that atom or in that molecule are bouncing around a lot. Another thing it can do, potentially, is release electromagnetic radiation. So let's say that that piece of matter had already absorbed electromagnetic radiation, or EMR, and it might release a form of EMR. That tends to happen when atoms are in an excited state, so their electrons are bouncing around, they're super excited, but it can't maintain that state for very long, so it's going to release that excess energy that it just absorbed. And then finally, matter can generally scatter electromagnetic radiation in some fashion. So that's going to do some form of bouncing off of it. Oops. So let's say that wave hits it, but it doesn't absorb it, it doesn't emit it, it just reflects, right? Or refracts it. And refracting would just be splitting it as a result of that thing traveling through. So it might split it into specific wavelengths. It depends on the material, if it's able to do that. All right, but spectroscopy can be used to tell us what specific pieces of matter are made of based on how it's interacting with that radiation. So basically, spectroscopy can be really fancy or really basic, but if you have a fancy one, there's going to be an emitter, and that emitter is going to emit some form of EMR. It depends on the wavelength, and the really fancy machines, you can specifically choose what wavelengths you want that emitter to be releasing. And it's going to aim that beam of EMR at our piece of matter that we're trying to analyze. All right, that matter is going to either absorb, release, refract, reflect something with that EMR radiation, and it's going to do all of that. And then there's this little spectrometer bit on the end that reads what happens, right? So if you emit a specific wavelength over here, and then it bounces off and you get different wavelengths over here, that's something that a spectrophotometer can tell you about. And it's going to give you a readout that tells you what the results are. And based on those results, you can identify elements within a sample. You can identify molecules within a sample. You can do a lot of very fancy things with that. Okay? So let's just go back to the reasoning why we're able to do this. What do we know already? We know that atoms have unique configurations of electrons surrounding their nuclei. And if you forgot what electron configuration is, I'm talking about this. The 1s2, 2s2, 2p6, that code that tells us where electrons are normally. All of the configurations that I've had you work with so far are ground state configurations. They're where those electrons normally like to be. If you have not pumped a lot of extra electricity through a sample, if you have not lit an element on fire, if you have not done a bunch of things to move it into an excited state. So again, these are ground state. And this right here, these drawings on carbon and oxygen are just a visual representation boiled down to a Bohr model, all right, of where those electrons generally are hanging out. The fact that all atoms are unique from one another with those unique configurations are why all elements respond slightly differently to interacting with electromagnetic radiation. And because they are unique, we can use their reactions to EMR to identify them. All right? So what we're going to be doing in this lab is this. If you took baby chem, you have already done this a little bit, but we're going to do it again, and we're going to do it a little bit cooler. So in our ground state, which is this bit on the left, we have an atom and it has electrons that are just chilling in its normal configuration. But if we add heat energy, and in our case, we're going to light them on fire, that's going to add our heat energy. And when we add that heat energy, our atom is going to move into a more excited state. Quite literally, let's say that this electron, pictured right here, let's say it's a 1s electron. It is going to absorb that heat energy, and it is literally going to hop up to a different placement. It could hop up into a 2s placement, or maybe a 2p placement, or maybe even a 3p placement. It depends on how much energy you're adding. But the point is that electron is literally moving farther from that nucleus because it absorbed the energy necessary to do so. But the equivalent for you would be me asking you to go attain a high energy state by sprinting around the track. You can't do that forever, right? Just like an electron cannot maintain a high energy state forever. Ultimately, what's going to happen is it's going to fall back down to its original position. And when electrons fall back down to their original position, they don't just fall, they have to release the energy that they absorbed somehow. And they do that sometimes by emitting visible light waves. Sometimes they might emit microwaves, sometimes they might emit X-rays, they might emit a lot of things. But a lot of the times it's light waves or ultraviolet light or something, and sometimes we can see it. All right, and that's what we're going to be observing today. So let's look at the electromagnetic spectrum. Here, in this photo right here, we have a range of the electromagnetic spectrum. And it's a little bit blurry, but I will rewrite some of those exponents. This on the right is 10 to the 8th. This on the left is 10 to the negative 16th. Okay, so this picture is arranged in terms of wavelength, right? So if we have a wave, there is a distance here to here, and that is our wavelength. Right? So on the right end of the table over here, we have waves with the longest wavelength, radio waves. On the left-hand side of the table over here, we have gamma rays, which have the shortest wavelength. Wavelength and energy are inversely related. So the waves on our low energy side on our long wavelength side have low energy. And our waves over on the left-hand side over here with our shortest wavelengths are the highest energy. All right, gamma rays, because they have the highest amount of energy, are also considered to be the most dangerous, whereas radio waves on the other end of the spectrum, really, they're just kind of chilling. They're low energy, they don't hurt anything, they exist, but that's, they're just chilling there. Right in the middle here is the visible light spectrum, in between infrared and ultraviolet. This is the only bit of the electromagnetic radiation spectrum that we can directly perceive. Obviously, there's a few indirect ways of perceiving these things, like for instance, if you get exposed to too much ultraviolet radiation, you get a sunburn, so you're indirectly perceiving it because it's damaged your skin, right? And we can use X-rays alongside of computers to take pictures of what's going on in our body. But really directly, we can only directly see our visible light, right? And so if we look a little bit closer at visible light, we see that there's a bit of a range, right? 400 on the violet side to 700 on the red side. But that doesn't mean that all red light is 700 nanometers in wavelength, but red light has a bit of a range within itself. And then we get a little bit of a range for orange and a range for yellow and so on and so forth. It depends on the exact wavelength where you'll fall, but we can categorize certain wavelengths as red light and certain wavelengths as orange and so forth. All right? We are going to be able to use two equations specifically to describe the properties of electromagnetic radiation. We're going to use wavelength, which I'm going to circle in green here. That Greek letter is lambda. It's this little funky upside down Y. For this particular formula that you're seeing over here on the right-hand side, the speed equation, wavelength must be measured in meters. If it's in some other unit, like say nanometers or picometers or whatever, you're going to have to convert into meters to use that formula. Frequency, this one right here, this little Greek letter, funky looking little v, is nu. Frequency is defined as how often a wave passes a point every second. So to understand that, you really need to consider the fact that waves are moving. Waves are never static. And so if we standardize one point and we can measure how many times a waveform passes that point per second, that's what frequency is. There are two units that you're going to see. They mean the same thing. I'm going to default to this one, seconds to the negative first, but again, hertz means the same thing. But the reason I'm defaulting to seconds to the negative first is because using that one allows our units to cancel when we use the formula. And then our last thing, speed, is how fast the wave is traveling. Sometimes you'll see it abbreviated as an S, sometimes you'll see it abbreviated as velocity or V, but ultimately it's just speed, and it depends on how you're talking about it, because technically speed and velocity are not the same thing, depends on your formula. In this particular equation, our unit is meters per second. If it's not expressed in meters per second, you're going to have to convert to meters per second. And then a constant value that you want to be aware of is the speed of light, abbreviated with the letter C, and that is 2.998 times 10 to the 8th meters per second. All right? Photons are going to be mentioned a lot. And photons are light particles, so they are going to travel at the speed of light. So if you see a problem where speed is not mentioned directly, but the term light or the term photon is used, that is the speed of light. All right? So this first equation, speed equals wavelength times frequency. I'm just going to use my colors to underline the different pieces of it really quickly to refer to later. We get, again, speed is equal to wavelength times frequency, and by looking at that equation, we can see how those variables are related to one another. Frequency and wavelength, positioned right next to each other on this side, are inversely proportional, which means that as wavelength increases, frequency decreases, and vice versa. As wavelength decreases, frequency increases. Both of those things, though, are going to be directly related to speed, which means as speed increases, our frequency is going to increase, etc. All right? This little waveform right here is just here for your reference. The topmost point of any wave is referred to as a crest. The bottommost point of any wave is referred to as a trough. And then the distance between those things, either trough to trough or crest to crest, is going to be wavelength. Amplitude here is just how tall it is from origin to crest, or we can also measure it from origin to trough. Okay, if you've ever dealt with sine waves before, you have absolutely dealt with these types of waves. The other equation that I want to talk to you about real quick is the energy equation. All right, and that's also known as Planck's equation. You'll notice right away that Planck's equation also has frequency in it. Right? So that's our link between these two equations. We can see that it is in both places. So if you ever have to use these two equations together, frequency will be your link between them. Planck's constant is h, and Planck's constant is always the same number. That's this number, 6.626 times 10 to the negative 34th joules seconds. And I know that this says joules slash seconds. It's actually joules times seconds. So I'm going to ask that you make that correction in your notes. It should read joules times seconds, not joules divided by seconds. On the other side, we see energy. All right? And energy over here is going to be directly proportional to frequency, and the unit for energy is always, always, always going to be joules for this equation. If your energy is expressed in not joules, you're going to have to find a way to convert to joules. All right? So now we're going to look at this practice problem here on the bottom. For that practice problem, you are instructed to calculate both the frequency, so I'm going to put that variable here, and the energy. I'm going to put that variable next to it as well, released by a photon. Photons are light particles with a wavelength of 650.0 nanometers. All right? Now, we are only directly given one specific number here, which means that that's the only number that we have, and so it's the number that we absolutely have to start with. So, looking at our two options for equations, the only equation that I see that has wavelength in it is this one. So I'm going to start with the speed equation. However, before I jump into plugging numbers in, I have to ask if my wavelength is in the proper unit. Nanometers is not meters, right? If we recall, our wavelength needed to be in meters. So the first thing we have to do is actually convert nanometers to meters. So we start with our 650.0 nanometers, and we're going to go all the way back to metric conversions. I know that I need meters. I know that nanometers goes on the bottom. Now, if you look at your metric conversion chart, meters is your bigger unit, and so for every one of my bigger unit, I have some amount of my smaller unit. So I'm going to go ahead and put a 1 right next to meters. That metric conversion chart tells you that 1 meter is equal to 10 to the 9th nanometers. So on the bottom, I'm going to put 1 times 10 to the 9th. All right? And my new wavelength value is 650.0 times 10 to the negative 9th. And that is now in meters. Please note that I did not bother to write that thing in proper scientific notation because at the current moment it's actually unnecessary. But if you just plugged that straight into your calculator probably gave you this. Those two things are the exact same number. The only difference is one is in proper scientific notation and one is not. All right? So now that I have done that conversion and my wavelength is in the unit I need it to be, I can now use my cool speed equation to get to frequency. Because I know that that photon is traveling the speed of light because it is a light particle. So I have speed and I have wavelength, and I can solve for frequency. All right, so I'll zoom in a little bit. My speed of light, as given up here, is 2.998 times 10 to the 8th meters per second. That is going to be equal to, according to our speed equation, wavelength, which I just calculated, 6.500 times 10 to the negative 7th meters, and then times my unknown frequency. I'm going to go ahead and divide both sides of that equation by the thing next to my variable, 6.500 times 10 to the negative 7th. So I'm going to take 1 second to plug that into my calculator. And what I get out of that is 4.612 times 10 to the 14th seconds to the negative first. So let me remind you why I rounded to that place value. The reasoning is because my wavelength had 4 significant figures. So my answer should have 4 significant figures. And the reason that I'm using seconds to the negative first as my unit is because it is frequency, and that is one of the acceptable units for frequency. Not only that, but when I did that division, my meters canceled out my meters, and I'm left with divided by seconds, and another way you write that is seconds to the negative first. All right, so pause for the overhead announcement.
Today at lunch in G3. Again, Best Buddies is meeting in G3 at lunch. Thank you.
All right, so step 1 of that problem is done. I have calculated my frequency, but I'm not done because I also need to calculate my energy. That's another thing that problem asked me to do. So what I'm going to do is I'm now going to take the frequency that I just calculated and plug it into the energy equation, right? I don't know what energy is. I am asked to calculate it. So I'm going to say E equals Planck's constant is given already. Planck's constant is always the same number, this. So I have 6.626 times 10 to the negative 34th joules times seconds. And I am going to multiply that by the frequency that I just calculated over here, by my 4.612 times 10 to the 14th seconds to the negative first. All right? Now, I'm going to take another second and plug that into my calculator. And out of that, I am going to get, let me switch colors. The energy is equal to 3.056 times 10 to the negative 19th. Now, the unit I'm going to stick on that is joules, because that is my energy unit, but also multiplying by joules and dividing by joules, or not joules, sorry, seconds cancels out those seconds, and that's what I'm left with. I'm left with joules. And this is my second answer. So, you should have watched this video so that you can successfully complete the notes calculations. If you have any questions, please let me know.